In the last video, we discovered one of the most famous equations in science, F is equal to ma. But this equation hides a much deeper question, that is, what exactly does a force change? For example, if I apply force onto a ball, its velocity changes. So is force changing only velocity? Let us investigate. Say there are two objects, one a tennis ball and a truck. Both are moving with similar velocity of 10 meters per second. The amount of effort required to stop the tennis ball is much lesser compared to stopping a truck. So if force alone changes velocity, then these two objects should not possess the same amount of motion. If velocity alone cannot describe motion, then perhaps the answer is mass. Let us see that also. Suppose there are two identical trucks of equal mass. One is stationary and the other is moving. As you can guess, the amount of effort required to stop the moving truck is far greater than for the stationary truck. So mass alone cannot describe motion. Here nature is forcing us to ask a new question. What single quantity becomes larger when either mass or velocity increases? It cannot be addition of these two quantities, since if that was the case, then when velocity is 0, then the amount of motion is clearly large in the first case. It cannot be division also, because a large mass would make this quantity smaller. So the only logical method available is to multiply these two quantities. But another question arises. Instead of velocity, can it be speed? Let us investigate again. Say there are, in the first case, considering speed, if we describe motion using only speed, then the quantity of motion simply adds together. And when through observation, when these objects are supposed to be stationary after their collision, in this case, mathematically it seems that the system should move, which is not the case in reality. What Newton did was he introduced direction into this equation. He gave a negative sign for an object that is moving towards the left. And now this system is balanced. So it shows that nature clearly cares about direction. Speed doesn't, but velocity does. And that is why this quantity called as momentum is mass times velocity. Direction is built into the quantity itself. Now these collisions begin to make sense. Object, exchange, momentum, gain momentum, lose momentum. The stronger the interaction, the larger the change. But suppose there are two identical pushes producing the same momentum. One push lasts for 1 second and the other lasts for 1/10 of a second. So both are producing the same change, but in different time periods. But are the forces same? Of course not. So force cannot simply measure a change in momentum. It must measure how quickly momentum changes, because a small force over a large period of time can produce a change. However, to produce that same change in a shorter time, you require a massive force. And in mathematics, if you ask how fast is something changing, the answer is given through derivatives. But one needs to know that when Newton started his investigations, this method was not yet invented. Newton developed what he called as fluxions. A changing quantity was called a fluent, and the instantaneous rate of change was called its fluxion. In modern day, we call it as derivative. Newton did not think that force needs to be differentiated. His reasoning was force changes motion, motion changes continuously and not in jumps. That is why his second law is written as how rapidly momentum changes at each instant and not just over a finite interval. And the mathematical language that describes this instantaneous change is called as calculus. See, Newton here did not use calculus because it existed. He helped create calculus because physics demanded it. We didn't begin with an equation, we began with observations. We observed velocity, it failed. We observed mass, that also failed. We observed speed, that too failed. But momentum survived. And the only quantity left that could measure force when time entered the picture was the rate at which momentum changes. And that is why Newton's equation is written as instantaneous rate of change of momentum. Now observe something. Suppose if mass is constant, then this equation becomes mass multiplied by rate of instantaneous rate of change of velocity, which in other words is known as acceleration. And now the equation becomes F is equal to ma. The equation that we have memorized all our lives was never the fundamental law. It is simply the special case of Newton's deep insight. Force is not the cause of acceleration. Acceleration was merely one consequence. Force is governing something more fundamental, and that is instantaneous rate of change of momentum. And that is Newton's true second law. We often say that Newton invented a law. However, the truth is even more remarkable because he had to invent new mathematics before he could even write the law down. Physics demanded a new language, and that language became calculus, and together they changed science forever.
If you see physics differently now, subscribe to Beyond Equations. Like this video to help others discover it. Until next time, keep looking beyond.